Okay, let's go ahead and zoom out. Oh, too far. So you should have drawn yourself a good representation of the electromagnetic spectrum. What I want you guys to get from this is that it's a wide range of different radiation. We're not talking about ionizing radiation, so not all of this is dangerous radiation. But we're talking about the differences is basically the change in that wave. The longer the wavelength, the most different the wave is going to be. For visual light, that's going to be the difference between color shifts. Okay, so let's get back to the notes real quick. So again here, radio waves. This diagram shows how big the wave is. So this is 10 to the 6th power. So radio waves would be 10 to the 6th power to a meter wide. And I don't mean every radio wave, but the different wavelengths. All the way down to the smallest, which is our gamma wave here, is 10 to the negative 18th power on the size of the wave there. Now, all electromagnetic waves, you're writing this down on 3, all electromagnetic waves travel at the speed of light, which is 3.0 times 10 to the 8th meters per second. All electromagnetic waves travel at the same speed. All of them. Every last one. Write that down. Right, so all electromagnetic waves travel at the same speed. They all travel at the speed of light, which is really, really, really fast. It's 300 million meters every single second. So if I were to ask you a question like, how fast do microwaves travel? What would you say? Go ahead and just shout at the screen. I didn't hear anyone shout at the screen. You should shout at the screen that microwaves travel at the speed of light, because they all travel at the speed of light. Every single electromagnetic wave travels at the speed of light. So microwaves, they travel at the speed of light. So if I have to ask you, X-rays, how fast do X-rays travel then? If microwaves travel at the speed of light, well then how fast would X-rays travel? If in your head, or as you were shouting at my screen, you said they travel at the speed of light, Mrs. Grether, then that would be correct, because they all travel at the speed of light. What about visible light? What about colors? What if I had a color flashlight and I was flashing it across the room, and then somebody had a clear flashlight that was just white and they were flashing it? How fast would those two go? And the answer is they all travel at the speed of light. What about UV radiation? UV radiation? How fast does it travel? If you said it travels at the speed of light, you would have been right. So the speed of light is so fast that at that speed, the speed of light at 3.0 times 10 to the 8th power meters per second, you could travel around the entire world 8 times. Now, light wave characteristics, even if it's a low frequency wave, it's really, really spread out, that does not mean it travels slowly. Radio waves are really long in their wavelengths, and by long I mean this distance between one peak to another. It's still traveling at the speed of light, no matter how stretched out that wave is. Now, if I were to look at a high frequency wave here, where I've got the waves really, really close and compact, that wave is not traveling faster. It is just closer together. It is more compact. Now, the same thing happens with sound. A low frequency sound is going to be a sound that's very stretched out. But a high frequency, it can still be slow, but it's very high pitched. So a high frequency, if you were looking at my voice on a computer, you would see it look more like this red frequency down here below, while the low pitch would look like this blue stretched out wave. The same exact thing happens with light. All right, so let's talk about some of this stuff. UV radiation, how it affects us is, I'm sure some of you have had this, and this person is apparently uber white because she is so white that she got sunburned this badly. I can't understand what happened to her, but apparently she should wear a sheet at all times, or maybe a parka when she goes outside. It causes sunburns. But one interesting thing is that bees actually have the ability to see into the UV range. So we look here, this flower here on the left is what we see with our visible light. This is what your eyes would see looking at this flower. The same flower, when we expose it to UV radiation, this is what we see. We see a dark landing pad for bees to come and enjoy the nectar, honestly. So we see this with a lot of different flowers that are specifically seem to be flowers that bees like. Another way we use electromagnetic radiation is in an MRI machine, a magnetic resonance imaging machine. Now, I don't know if any of you have had an MRI before. I know I have, but MRIs are really good. They're kind of like an X-ray, but they see the squishy parts of your body. So you can look at the brain matter. We can see tumors inside the body. You can see this guy's tongue. It's kind of cool looking. But it uses radio waves and a magnet to be able to create images of the soft tissue of a body. All right, now, almost every one of you probably has used a microwave oven in the past. We kind of already talked about this. Microwaves, the wavelength is just perfect for that water molecule. It causes the water molecule to vibrate violently, heating it up, causing that movement energy, the kinetic energy, to change to heat energy, and this is what cooks your food. All right, so another way we use electromagnetic radiation is through radar. So radio detection and ranging. So this cop in this picture, basically what he's doing is he's shooting a beam of radar at you, a radio wave at you as you're coming at him or as your car is coming at him. And the difference of the wave as it comes bouncing off of that object back into the machine helps the machine calculate how fast you're moving, what speed you're going. And it doesn't matter if you're moving away from him or towards him, it will calculate the speed in which that radiation has changed. All right, so another thing is infrared radiation. Now we think of infrared radiation mainly as heat, but it's not all heat radiation. Heat actually on Earth doesn't transfer through space. It has to transfer from molecule to molecule. But other infrared radiation does transfer very well through space. Now we use different cameras to look at objects in space, distant galaxies, stars, many different things, because when we use the different cameras, it gives us different information. An example here is this galaxy. Up top, we have the visible light. This is what you would see with your own eyes. And then down here below, we have the infrared image of the same exact galaxy. The infrared image tells us a lot more about the star density inside of this galaxy. The above image is lighting up the visible light of all the dust and gas and everything that's around inside of that, while the infrared image down below shows us more realistic view of where the stars are located in this galaxy. Now, we still have some of the dust lit up as well in the second picture, but it does give us a cleaner picture of where, especially in this arm area here where it seems like there's almost little to no stars, and here we can tell that there are many more stars just based by our infrared camera view. Okay, so let's move on to the next thing. Apparently my computer's stuck. There we go. Okay. So the visible spectrum is just one very tiny band of the entire electromagnetic spectrum. So when you see a rainbow, you see all those colors. What we're actually seeing is the visible light that the sun is sending to us. Now, the sun sends us white light. We call it white light because when you have all the colors of light combined together, it does something opposite of what you think it does. In paint, we mix all the colors together and makes it as brown or black color. But when we take all the colors of light and mix them together, in light, it makes white light. And when the light comes through and hits a raindrop, what happens in that raindrop is actually splits the light into its different wavelengths and causes a brilliant display of all this light coming in into the different colors of the spectrum. Now, if you guys have more questions about rainbows when I get back, don't forget to ask me and we can talk about them, but that's all I'm going to go over for right now. All right, so spectral lines. We're going to focus for a minute on spectral lines because your lab that you're going to do is going to see these. You're going to actually examine them, and I want you to understand what they are when you look at them. Right now, we're looking at a hydrogen absorption spectrum, which is on the top, and a hydrogen emission spectrum at the bottom. The weird thing about chemicals is they all have like their very own fingerprint. Not a real fingerprint, but a color print, I guess I should call it. Hydrogen, no matter what's going on with hydrogen, will always absorb or emit colors in the exact same wavelengths. So here we've got hydrogen absorbing violets, blues, and this one very distinctive red band. Hydrogen will always absorb these same exact colors every single time. Now, in an emission spectrum, hydrogen, when it emits light, it may emit light because we're lighting it up, giving it a lot of energy. It's in the sun, it's glowing, it's in a light bulb. It will emit the same exact wavelengths of colors every single time. When we look at colors with special diffraction gratings, this is what you're going to use, it will split the light into the colors that make it up. And that's what we're looking at here. We're seeing the rainbow of this chemical. Now, everything is made up of chemicals. Your blankets are made up of chemicals. Your cat is made up of chemicals. Your ceiling fan, your water, your face, the air, everything is made up of chemicals. And every molecule has its very own fingerprint. Now, in this lab that we're going to do, you are going to look at the fingerprints of all these different chemicals. You're going to look at hydrogen. You're going to look at a few other light bulbs. And you're going to take a look at sunlight as well. So this is the device you're going to be using. This is called a spectrometer. Basically, you're going to be looking in this end here. There's an eyepiece here. Some of you will use a box one, but most of them look like this. And then there's a slit here on the bottom. When you're using this, you will be able to see these spectral lines. We're actually going to be looking at emission spectrums. We will not look at any absorption spectrums. We will only be looking at emission spectrums through this device. What you're going to do is you're going to take the slit when looking through the eyepiece, and you're going to line up the slit perfectly with the light from the light bulb. Now, this would be very important on the hydrogen light bulb. It's not a very bright light bulb, so you want to make sure you have that beam of the hydrogen perfectly lined up with the slit in the bottom of your container. Now, when you're looking at it, you're not going to look at the slit, but you're going to look to the left or the right, not both, because they're just a mirror image of each other. You're going to look at the left or the right. This is where you're going to be able to see your emission spectrum. This is where it's going to show up. This is where you're going to be able to see the chemical rainbow of your spectrum. Now, everybody should go ahead and put away your notes, and you need to get out in your assignment packet. It is page 33, the assignment on page 33. Go ahead and grab your assignment now. All right, so if you haven't found it yet, the assignment looks like this. It's called the Spectroscope Lab. Now yours is not in color. Yours is in black and white. Sorry, I can't afford to print color for y'all, but it would be very pretty, and it should be. Everything should be in color, but it's not. So, deal. So once you have the Spectroscope Lab out, what I want you to do is I want you to go through this lab. I want you to read the introduction, read the instructions, put the video on pause for a second, and then we're actually going to talk about what's at the bottom of this page before you guys get started. So read through all this information, and then we're actually going to talk about this before you start. Okay, so when you go and you start looking at all these light sources with your spectrometer, or sorry, spectroscope, you need to get a few very specific light sources. Sunlight is going to be one of them. Hydrogen is going to be another. So the sunlight is that hole that's cut in the paper on the window. Go ahead and just aim your spectroscope at the sky, you'll be fine. And then you need to label 4 other light sources. So you'll go to a light bulb, it'll have a label, write down that label. If you don't write down the label, it's going to be hard for me to give you credit for that spectrum, because I won't know which light bulb that you actually got that spectrum from. So make sure you're getting it from the correct spectrum. Now also, you'll notice that not everything is a full rainbow. If you color me an entire full rainbow from 400 to 700, you will have done it wrong on almost every single one of these spectrums. You should not have a rainbow from one end to the other. Also, you'll notice that these numbers that are on there coincide with the numbers here: 400, 500, 600, 700, 800. That is because this is the frequency or wavelength in which these colors reside. Now, turn to this front page here and try to get this in my view so you can see it as well. But this image here, I know yours is not in color, but it shows you how these colors line up. Now on yours, many of the light bulbs are going to only have a few bands of color. You need to make sure you have them in the correct wavelength category. I know you can't see the colors on yours, but if you look over here to the right of this table, you will see that violet extends from 400 to 420 nanometers. Indigo is 420 to 440. Blue is 440 to, I'm not sure where it goes, it went away. But these numbers coincide with these numbers. So if you have a purple, you need to have it somewhere between 400 and 450. If you've got red, it's going to be around here, the 700 range. So here I've got green. Green's 490 to 570. I've got orange 585 to 620, and red to 620 to 780. Use this chart to help you figure out where you need to draw those lines. During this observation, many of the points for this assignment is going to become from your ability to make very precise observations of where those colors are existing in the spectrum. If you have green line and you have it drawn in the 800 spectrum, you will not be getting credit for that because you have done it wrong. 800 is red. So be patient. look through the spectroscope, see the color it is, try to find that on the chart, and then find that color in that zone and get it drawn correctly. Now, if a color crosses many bands, like it looks like a really fat band, you're actually not looking at one big fat orange slice or one big fat red slice. You're actually looking at many different wavelengths of the red different colors. So you'll actually have so many lines that it looks like it's a solid block. Now, one last note about people with glasses. If you have glasses on, the best thing to do is look at the spectroscope under your glasses, to take your glasses off if you can see well enough like that. If you don't, you're pretty much going to see only rainbows. Hopefully your vision is clear enough where you're going to be able to see approximately where these lines are. But yeah, a lot of times when I've had people with glasses try to do this lab, they try to look through the glasses with the actual spectroscope, and all they see for some reason is just a bunch of rainbows. I don't know if it's exterior light coming in and bouncing off your glasses, going back in. I don't know what it is, but if you have glasses, you're going to have to play with it a little bit and see if you can get the spectroscope to work with your glasses or just avoid them at all. Now remember, you need sunlight, you need hydrogen, and then you can choose 4 other light bulbs in the room. Alright, so on this assignment, if you should get so far as to take all of your observations of the light and you get them drawn in properly, you are going to go on to answer the questions. You will not go past question 4, however. There is stuff in this lab that we have not discussed in class yet, and is going to be very confusing for you if you move on before we get there. So if you get to question 4, answer question 4, and then do not move on beyond that. Alright, so again, get hydrogen, get sunlight, and 4 other samples. Alright, read the directions again, and good luck. Substitute. It is now time to turn off the lights in the room and turn on all the lamps on the back tables. Alright, I will see you guys soon.